So the title of this talk is Android Safety Net Hardware Back Attestation. Now I'm going to introduce all the core concepts and start at a low level and try and make sure that everyone can understand, hopefully, and follow along, even if you've not got a developer background or you're not in security, etc. Specifically, we're looking at what I'm referring to as bypassing the impossible, and I'll explain why I'm referring to it as that as we go. So a little bit of an introduction to who I am. I know you're all sick of seeing who I am being at the top of a slide, and it's a bit stereotypical, but we're here now. So I'm a security researcher and consultant. My day job is actually in consultancy. However, during my hobby time, my free time, etc., I'm always hacking something, trying to break something new, or generally just doing something that I find fun, which happens to be typically around computing. I have a background in full-stack development as well, with around 10 plus years just of my own personal life, programming at a minimum, with fluency in far too many languages to count. And my current hobby project is trying to run Doom on an HDMI adapter. And specifically, this is an Apple little Haywire adapter that plugs into your iPhone. And it has its own system, it has RAM, memory, etc. A lot of weird, quirky limitations. And I'm trying to exploit that so I can get Doom running on it and plug it in and make it persistent as well. All the necessary areas of expertise are there. I have to piece together the pieces though. It's going to be good fun. Hopefully the next talk will be on that. Responsible disclosure, just for everyone here. This has been disclosed to Google. I haven't had confirmation yet if it's a unique vulnerability. As far as I know, from Google, search on the web, etc., no one else has done something like this, attempted it, etc. The source code is not available yet. There's two reasons for that. A, I don't really want anyone exploiting it before it can be fully patched and remediated, although technically you could try and do your own implementation, but you run into a few hurdles along the way. And secondly, source code's a mess. I've tried my best to make it clean and readable, but I've been tweaking it, and the last few days have been a real rush to try and make this as functional as possible. So what is Safety Net in Android? Well, it's essentially a module or a library that your application can load, and it attempts to do a few key things. And I'll cover this in the next slide just so it makes a little more sense of reference. But it's only supported on Google Pixel devices, and that means essentially that our audience for this would be, for instance, Google Pixel 4 and later, specifically because that's when they implemented hardware attestation, which uses part of the actual system to perform the process. It's theorized to be impossible to bypass. Take this with a pinch of salt, though, because the majority of these people are self-proclaimed experts on Twitter who believe that it can't be done and no one should ever attempt it and you're stupid for trying, or something along those lines. As we know, don't tell hackers something's impossible, because when you do, they get furious and they start breaking things, and then suddenly you've got an exploit in your hands. So the use of Safety Net that I just touched upon, you can use it for majority of a variety of functions, particularly verifying applications installed on the device. So, for instance, if you have malicious applications or something that's not approved by Google, a safe browsing API, which refers to verifying URLs that might look like they're potentially phishing or dodgy domains, strange characteristics, etc. But that's prior to when a user visits it, and that uses Google's database, essentially, of what they consider good and or bad. A reCAPTCHA API, quite standard things, that's proven that you're not a robot. And then finally, and this is what we're actually interested in, the Attestation API. So, attestation on Android means checking the device's state and a variety of facts about it to determine things like, is it rooted, or has it been tampered with, has the code execution been changed? The idea is that banks, social media, games, etc. can use this and essentially say, yes, this device is in a good state and we continue to operate on it. It's quite straightforward to actually implement for a developer. You do require an API key from Google, which can be obtained in all of around 10 or 15 minutes. However, I was lazy, so for my purposes, I stole someone else's key. And here's a little example of how it works at a kind of high level. So on Android, applications typically have a naming convention of something like com.example.myapp. And this is actually an APK, so that when you click on the settings app, that's an individual APK. When you click on photos, that's another individual APK. So your application imports the safety net library and the necessary dependencies for it. That in turn facilitates speaking to Google Play Services on the device itself. And then Google Play Services speaks to Google's actual API, which is remote and on the internet. And this API takes the blob of data you've sent, which we'll cover in more detail exactly what that is. It signs it, checks it, etc., and returns something you can actually use to say, look, this device is secure, it's being verified by Google, and you can essentially verify the signature of that on your own actual web server. So there on step 3 is a web server for the application, and you can think of this in a theory of kind of like a bank that might have the application, they test the security of the device, and they send the token they get back from Google's API with every single request, and that's verified all server side, which essentially limits and removes the factor for you being able to bypass client-side security, because you can't use the internet functions that are sort of dependent to do what you want. So an example of how this is actually implemented is quite simple. Before this, in the main class of the actual program, we have about 3 or 4 imports, which just grab some safety net utilities. But let's break down this code for people who aren't Java developers and try and understand it a little bit better. So the first lines say, I want to create a safety net client and I want to instantiate that. You'll see in the brackets given is an argument called tag, and we'll cover that a little bit more later, but essentially the context of the application, which is a way for something to retrieve details of the app, like its name, what it can do, what kind of activities it exposes, etc. So we're giving the API some reference to our app, and then after that we're asking it to perform an attest function. And this attest is actually a task, meaning it's asynchronous, it takes a while to return, it doesn't immediately return, so we actually have to then call or set up essentially a listener or callback for it. And this says that when the task is finished, the safety net attestation task, we want to call the onSuccess callback with our attestation response included. And then we can grab from that attestation response object within the callback a JWS token. I'll detail a little bit more of what that is in the next slides. And then finally, we just have a simple debug message, just so we as a developer know it succeeded, we should have something back, and now we can work with it. So, I alluded to this before. Google Play Services speaks with Google's API. It uses HTTP traffic, and that essentially includes a whole bunch of data about the device, which Google can then verify to ensure it matches what its expectation would be. Certificate pinning and validation is enforced, so we can't sniff it on a non-rooted device, meaning we have no visibility into a rooted device, and the rooted device doesn't quite behave the same as an unrooted device. For reference, routing here refers to breaking the constraints of an Android device, so you can run your own code, etc. And as I said, the response proves that our device is rooted, and I'll show you what that looks like shortly. This is an example of an actual request to Google's API. In red are the things you need to sort of look at and be aware of. So we're speaking to the attestation's attest endpoint. Where it says alt equals proto, this refers to a proto buff wrapper around what's going to come back. We don't have to care too much about this, but it just helps us make sense of the data that's coming back. The host, again, is googlesapi.com. And then we also have 2 more pieces of information, and this is between seemingly random data, a load of random hex. This is the build date of the application that is trying to run the test function, and also the APK's name. And these are going to be very important later because of, essentially, we run into some hurdles with this and we need to try and modify what's happening in order to work with it. The response back from Google's API, so after we've asked it to attest to the device's state, given the data we've supplied, is something like this. So you see those first 2 red bytes, that is part of the protobuf wrapper. And I believe that I just say you can expect the following response to be X length. Now, the keen-eyed among you may notice the beginning of that message, which is EYJ, quite standard for JWT tokens, JWSs, etc. So, if anyone is not aware, a JSON Web Token, JWS, is a base 64 encoded data structure delimited by full stops. So the structure you'll be looking at will be something like a header, a full stop, a payload, a full stop, and then a signature. Each one of those individual components is base 64 encoded, meaning it's represented by 64 unique characters to encode the data. We are only interested in the payload for this. And in order to actually decode a JWS token, just for reference purposes, we can grab the payload from the middle, code it base 64, and look at the data. So what do we get back? Well, we get back something that looks a bit like this. We get an initial nonce token, which is typically something like 32 random bytes of data that the calling application, so for instance, com.example.myapp, included within its request. We get a timestamp as well, and then we get two more elements which we need to care about: CTS profile match and base integrity. I'm going to break down what each of these actually mean and why we actually have to care about them now. But we also see, because this was run on a routed device, the advice back from Google is restore to factory ROM and lock bootloader. And then the evaluation type, just so we know we're on the right track here, is hardware backed. And what this means is when the attest function was called and occurred, it actually used the trusted execution environment on the phone, which is part of the system on chip, the SoC, essentially your main processor, a variety of other pieces of very important technology within the silicon itself. It's very, very difficult to reverse engineer or break things at hardware level, and typically is more or less unheard of. Currently, we always target software vulnerabilities whenever possible. So within this, we're actually missing 2 bits of data, and there's a very good reason why it don't appear in the JSON. I can go back to this so you can see there is no APK digest or package name included in what we got back. And there's a good reason for that. So, if when you perform a test, the basic integrity is not true, then Google doesn't even bother to attempt to verify your device. It makes the request to seem like stuff is happening, but it just throws it out really, and it doesn't care. Basic integrity refers to whether or not the device has presence of specific characteristics that suggest it's being rooted. So typically this would include magisk, used for rooting devices quite commonly, binaries like SU, S8 or bash, etc., and modifications to those binaries, along with modifications to the bootloader. If any of that is detected, then basic integrity will fail, and this one will come back in our data. For reference, a complete data set would look something like this, where we have an APK digest in SHA-256, which is a hash of the APK itself. And then we have a package name, which tells us who actually requested this data to begin with. So what does a safety net failure look like? Well, this is an application on the Android Play Store called Safety Net Test. You can download this yourself and you can test it. I believe SafetyNet is only supported by Google Pixel devices, so if you don't have one, you won't be able to find it, or it probably will just say it doesn't work. It may also quite well just do software-based attestation instead and completely skip the hardware portion, which is the bit we actually care about. So a failure here says that our CTS profile was false, base integrity was false, and we get the advice back. So it didn't pass SafetyNet. The key values, as I mentioned, were that CTS profile and base integrity. So CTS refers to Compatibility Testing Suite, and what this means is the data you send to Google's APIs with your device's state do not match what they believe a factory restored or safe device looks like. So in other words, it had something that had been modified, hashes didn't match or person being changed. Oh, and basic integrity also outlines whether or not you are using an emulator, for instance. So Google are very focused on avoiding you being able to emulate safety nets, so you can't easily reverse engineer it. Although, as we see later, they did a very bad job of that. So, as a developer, what can we do with the JWS token we get back from Google's APIs? Well, we can verify it on the device as a really basic and quick check to say whether or not the device is in a secured state. But this can be bypassed with client-side hooking or general modifications to the APK itself. Otherwise, we can also send the request. We can send a request to our server with the JWS included. So, for instance, as I said, a banking application, when you make a payment, might want to include a JWS. Your bank server verifies it and says, yeah, the application is in a secured state, so I'll let this payment proceed. This is probably not being performed by a malicious actor. And you'll see safety nets actually used a lot in banking apps, social media, and games. Particularly things like Pokemon Go, I believe, use safety nets. So how does safety net really work at a more technical level? Well, the client imports a library, we know that. And then Google Play services actually download the safety net runtime binary, which is a jar file on the fly. That binary is being obfuscated. It's very difficult to read, and it is difficult to actually reverse engineer as well. In fact, it errors out a lot of attempts when you're trying to reverse engineer it. The utility, as we said, utilizes the trusted execution environment within the SOC. So already we're facing hardware limitations potentially where we're not going to be able to dig into it quite the way we want, and we're not going to see everything that's going on. And the device's state is actually verified, and the collected data you get back from the device's state is then signed with a private key by the trusted execution environment. So what that means is, unless we have this private key, we can't make our own data. And we also don't really know what data looks like to begin with because it's all encrypted. Our attack audience, so people would actually want to bypass safety net. That looks like security researchers like myself. So when I'm doing application testing, quite often I'm going to try and test an app. It's going to do a safety net attestation, and then suddenly I can't test it because it knows that my device is rooted, or I have a very limited foothold to essentially test it on a non-rooted device. Users wanted to run apps on rooted devices, so maybe you wanted to get some more freedom, you want to get away from platforms like Google and try and get rid of the bloatware or what you might consider spyware potentially and various telemetry data. And then finally, and a group we wouldn't really want to support would be pirates and cheaters. So mobile games where you might want to try and cheat to get yourself advantages. Pirates trying to rip apps that cost money off the App Store, no longer support the developer, or potentially even implant malicious payloads into those applications to compromise users who attempt to use them. So that's 3 key audiences. And then the attack surface we've got. So if we want to look at exploiting this, bypassing safety net, or generally just avoiding its use in applications, what can we do? Well, we can look at person-in-the-middle attacks, which rely on having a device connected to a network which you control, and you intercept the data going back and forth to that device, which then in turn goes back and forth to Google. This isn't really possible because of certificate pinning and validations enforced over a TLS connection, so we don't really know what's going on behind the scenes, at least with any ease, and we can't intercept and change things because of there's signatures involved anyway, which validate the actual data itself. We could look at client-side runtime hooking. However, this usually needs to be implemented on a case-by-case basis. In every single application, you want to bypass safety net in, which is essentially what already happens, but it's a sort of unfavorable option because of we don't want to do it on a case basis. We want to achieve this globally. We can replay safety net responses, but you saw there was a timestamp involved there and a unique value in the actual response. So when that's verified, it won't match what's expected, and the timestamp will be essentially out of the limits defined by the app. And then finally, we could just steal the private keys from the hardware and sign our own data. The issue is this has happened in the past, and Google simply decided to revoke certificates, do a system update, and now that doesn't work anymore. The ability for that to actually happen is so few and far between as well that it's very unlikely to actually keep stealing private keys and compete with Google to keep signing his data for such a simple purpose. So, ruling out this tax is what we've just sort of achieved here. We said each one of them has different drawbacks, so what's the best option here? There is one that we can kind of come back to, but implement in a different sense. So, if we look at client-side hooking, ordinarily this would still fail because the hardware is responsible for actually achieving the attestation and defining your device's state. But if we use 2 devices, for instance in this diagram concept here, so we have a good Android phone which is unrooted and runs our safety net server, let's call it, and this actually performs all the attestation on our behalf and then returns the data. And the Eagle device has the attest function and the get JWS result function both hooked with a framework. So when we attempt to do an attestation, the good device conducts on our behalf, we take the response from that, which is valid because the good device is in a known and good state, and we use that in our Evo application to make it appear as if that's actually a good device. At least that's the theory behind it. So there's a framework called Xposed on Android. It's a runtime hooking framework for client side. It uses Java, you need a module loader for it, and it's very difficult to get up and running initially because it's quite outdated and documentation lacks. But if you do get it working, you can hook functions successfully, including these attest functions and JWS results. There are some limitations with it, namely, it only really works with Java, unfortunately. We can't currently hook Kotlin applications, which are quite common for developers of writing. And the standard workflow, like I sort of showed up before, might look something like this for Attestation. The client app calls the test method, the task happens, we get the callback, and we return the JWS. But a standard workflow with Xposed in between might look something more like this. The client application attempts to call the attest function, but that has been hooked by this Xposed framework, and we actually jump to a little trampoline, sets up all of our parameters, our data, etc. Then we jump to a method called beforeHook method, and this is within our Xposed module. That enables us to run any code we like prior to the method that you're targeting being called, at which point the original method is called to preserve the integrity and workflow and make the application look legitimate. And then finally another after-hooked method is called, which enables us to clean up or do anything else. After that's all done, the actual original return value can happen, and as far as the application knows, it's not been hooked and everything's perfectly normal. So working out what and how to hook. Well, when we implement SafetyNet in our own application, we need 3 libraries: SafetyNet, SafetyNet API, and SafetyNet Client. So we know those packages are somewhere, either on disk or downloaded at runtime, and we can hook those and hopefully get the method we want. It's a little bit more complex than that, and I kind of explain as I go. So the SafetyNet binary, you can find the public implementation of it, the interface, on your device under data/app under an APK file. Now, it's actually referred to as Google Mobile Services, and Google Play Services, Google Mobile Services are both interchangeable. But if we dig that actual APK out, containing the SafetyNet implementation, we can convert it to a jar file that we can decompile. We can use an application like JDGUI, and we can analyze it and then attempt to build our hooks around the data we're expecting. So, for reference, the SafetyNet class once decompiled is a little bit like this. We have its class name, SafetyNet. We have a field that's declared as static, which is SafetyNet API, and we'll come back to why it's important after. The getClient function, so this is something we were calling earlier with our application. And we have a static initializer at the bottom, which sets the SafetyNet API to be equal to an internal class. This internal class, if we actually dig it out, is essentially just an obscured implementation of the class that contains the real code, what happens behind the scenes, etc. And then the same thing we can see for the SafetyNet API class. So this is the actual implementation I just referred to of the SafetyNet API, and we see there's a test function and a ZZA function. So the ZZA is what we're actually going to hook a little bit later, because it's a static function and it's actually called by a test just there. And the reason we're hooking this one instead of the test function is because for some reason Xposed fails to hook the test function, likely because of it's an instantiate function and the method to hook it changes a little bit, but those exact details aren't too important. When it comes to actually hooking this, we end up with something that's a bit like this. We have an interface for the class, we find the class based on the knowledge we've just got, which is SafetyNet. We then grab the API class from the actual previous field, which is SafetyNet API, that one at the top just there. So we grab that field, and then we hook the method ZZA, and then we can use those privacy knowledge, which is before and after something's actually hooked. So what can we do once we've hooked the getJWS result function with SafetyNet and the attest function with SafetyNet? Well, we can make a web request, like in our diagram, to our good device, and we can ask it to attest for us and give that data back. as part of the get JWS result function. And let's just sort of revisit this hurdle. So you would think in theory, we've got all the pieces of the puzzle and we can put them together, but we run into an issue. Remember before when I said that assuming basic integrity passes, there would be a field called APK package name and APK digest included, along with a certificate chain. Well, on Android, when an application makes a call to safety net, a mechanism, which I couldn't actually determine unfortunately, is used to pull data of that APK, that application, and use it as part of your test function. And what happens when we actually send this data across this JWS to our server, our external service, our bank server, is they say, well, the APK name does not match the banking app. So for instance, com.banking.barclays is expecting that field to be present and is expecting it to match in its entirety. But because if we used another application of our own making on the device to essentially make this call instead, that's no longer going to match. And likewise with the SHA hash. So we can't just spoof the name, we have to spoof the hash as well. And then we'd have to spoof the certificate chain. So this is the first hurdle we run into. And as of yet, I haven't actually been able to bypass, unfortunately. I spent the last 2 weeks reverse engineering this and kind of doing my very best to try and make this work. And the truth of it is, it's very difficult and very time consuming. I wasn't actually able to bypass this last step, but I can show you a little bit of what it might look like once this is bypassed, and I do believe that it can actually be implemented. So, remember before, in the attest function, we passed a context called temp. Well, this is the context we're passing, where I overwrote the set package name and get package name functions. And the idea behind this was, well, if SafetyNet only knows about our application based on the context we pass, if we overwrite that and we make it return different data, surely SafetyNet should get different data. But the result of that appeared to be that, in fact, no, it didn't. And SafetyNet, unfortunately, is using alternative mechanisms which are quite difficult to dig out in this sort of obscured code base to determine what application is calling it, data regarding it, and also the hashes, etc. So an attempt was made, but ultimately unsuccessful, and I added log functions to these when I created them, but the logs never got called because SafetyNet never actually used our context in a way that I was expecting. But it is possible that with more refinement, there might be some alternative way to potentially hook this and ensure SafetyNet believes that we are the fake application that we're pretending to be. So let's look at the results back so far as a sort of very basic recap. We were able to hook the necessary methods to essentially try to bypass SafetyNet, so that gave us a good start. We had a very good understanding of SafetyNet and how it works internally based on our decoupling efforts and also our research in general. And then finally, a good insight of how the exploit could work in theory. Now, this is actually some screenshots of my setup that I had going. So you'll see on the left side is an application called SafetyNet Mod. This is running a basic HTTPS server. It performs the attestation, sets threading protocols, etc., and returns the data in that request from the good device. And then that data is, with our hooking methods we reviewed before, essentially injected back into the evil device, make it appear as that's what was expected. But you'll see the response we get it's very small, so it's also at the bottom. Response payload validation failed. If we look at the actual logcat, so the logs that the applications are producing, it will tell us that the APK name does not equal the expected APK name. So, for instance, com.example.myapp does not equal to our com.safetynetmod application that we made. And what this means is currently our proof of concept under attack is failing, but there is actually a glimmer of hope in this, and I do believe with some further research it can be made to work. Now, I want to sort of end this by saying this is a couple of weeks of research, and it's a very good start, and the ability to actually perform this attack currently relies on using the sort of outermost layer of safety net's attestation. But if we dig into those classes and we re-implement the core functionality, aka we speak directly to the hardware, and we tell it what our package name is, the data, etc., there's a very good chance that we can actually spoof this functionality at a lower level and return that data instead, at which point we'd have a functional exploit. I'm going to continue to actually attempt that and try and make it work, and hopefully the results soon enough will end up on GitHub or somewhere once Google kind of vets and triages the process and essentially signs off on, yes, we think we fixed this, or something like that. So, given all the information, are there any questions? Has anyone sort of had any,
That's a great cool thing.
Thank you.
How wide have you seen safety net being used very widely, given the diversity of the Android ecosystem and devices? I could just take a Samsung device and then it's not supported. How do these apps handle that case?
So, an application that doesn't have safety net support will look for some alternative means of testing the device. If I'm not mistaken, I think the software side of attestation can actually still be used on unsupported devices. So if it's just a Samsung device, they still use basic integrity. That's quite trivial to bypass nowadays. In fact, as just a very quick example, if we want to make a Google Pixel device use software attestation instead of hardware backed, we can just append a space at the end of its name. So instead of Google Pixel 6, it becomes Google Pixel 6 space. And that will make software attestation, which is currently easily and known bypassed. But in terms of how many apps are using safety net, there's quite a few. Like I mentioned, games like Pokemon Go, I believe social media apps like Snapchat, nearly every single banking app is going to try and make use of every single defense they can get. And at software level, the security is more easily bypassed. But when we're looking at a hardware module that's supported by Google and implemented by professional developers, the odds of being bypassed essentially get reduced. So it's very tantalizing for developers and firms to use this technology, especially since it's, as we saw, very easily implemented. Does that answer your question? Fantastic. Any other questions? Let's do the one at the back first. It's easier.
If this is following on the same vein as TPM attestation, because you're using the same device, they just pin the device specific certificate during the registration process, and that way they can test that device before attestation.
Well, they could change the workflow of it. As you saw, they are already kind of doing something like that, where they can't pin the device specifics because of every Google Pixel phone in the factory state should look fairly similar, and we don't know what devices users are using exactly, because we don't know the IMEI number or serial numbers of the device. What we do know is the APK that we've actually produced, the hashes of it, the signatures we're expecting within that APK. So if they don't match, then you can say, well, the device may be legitimate or not, but something's gone on in between there, where another application is attempting to fool us with a fake attestation response. Your question as well?
Okay. So the test that you showed with the 3 screens up there, that was testing, checking validating the data that came back from Google in the client-side application and the safety net test application. Mm-hmm. But you're saying that really you should be testing that server-side
exactly.
Every request that's made.
Yes.
Do you know whether most people that do test this server-side just check, is the signature valid, that's okay? Or do most people actually check he's got the right app? Because if they don't, then that would just work.
Exactly, yeah. So there's a very good chance that a lot of server-side implementations that are verifying this are done wrong. And if they are done wrong, or means to bypass it, suddenly become quite possible. The application I've got and listed here is performing an offline version of the attestation, or the validation of that. And it's actually simulating what a server would be doing. So that's picking out the APK name, checking the timestamp, verifying the CTS profile and basic integrity match. That should be what every server is doing, but this implementation on the server side is left entirely up to the developer, which means a myriad of logic bugs. And considering the complexity and sort of the lack of general documentation of how it should be implemented correctly, it means that it leaves a very big room of sort of error for the developer to incorrectly implement. So it's very possible, yes, that our attempt here at bypassing it could quite well work on Lloyd's banking app, Santander, or some other application where we believe it was secure, but no one's attempted this before.
You haven't tried that on any services yet?
No, I haven't, just for not trying to break the law too much.
Full time on that.
Fantastic.
5 minutes over, but it's always nice when you get questions that you can answer. So, a couple of minutes more, and we'll be swapping over and having another speaker. If you do have more questions, I'm sure he'll be available in, I don't know, somewhere in a hotel. It's not that big, you can't.
Yeah, you can feel free just to find me. I'm happy to take more questions.
See you all in a few minutes.
Okay.